Okay, welcome everybody. My name is Slavek Solecki of Cornell University. I will be the moderator of the session. It is my pleasure to introduce Andrew Marks of UCLA, and he will talk on measurable graph combinatorics. Please, Andrew.
Thanks, and thanks to the organizers for the invitation to speak. The topic that I want to focus on today is measurable graph combinatorics. And the idea of the subject is that many fields of mathematics naturally study combinatorial problems on infinite graphs, but often when we solve these problems, we'd like them to have some additional measurability conditions. Maybe we want to find a solution which is Lebesgue measurable, or Borel, or continuous. Here, when I say measurable, I mean in a general sense where we have some algebra of sets in mind, and we mean that the preimage of any open set is in this algebra. So the algebra of open sets would give continuous maps, of Borel sets would give Borel maps, of Lebesgue measurable sets would give Lebesgue measurable sets, and so on. So measurable graph combinatorics is the study of these sorts of problems, and they appear very naturally in many areas of mathematics. They show up as the problem of finding factor of IID solutions in probability theory, in measurable equity decomposition problems like Tarski's circle squaring problem, which we'll come back to at the end of the talk. Laskovich in the late 80s first started proving some theorems in about measurable matchings motivated by equity decomposition problems. In ergodic theory, these sorts of problems show up, for example, in the theory of cost. In topological dynamics, we'd like to show that an action of a group is what's called almost finite. We need to find Clopin tilings of these actions on zero-dimensional spaces. We'll also come back to hyperfiniteness and treeability later in the talk, trying to find subtrees of graphs which span the graph, or witnesses to what's called finite asymptotic dimension. And in the theory of combinatorics itself, there's this notion of graph limits. We can have a sequence of finite graphs that are increasing in size and make sense of what it means for this sequence to converge to some infinite graph on some standard probability space. And combinatorial properties of the finite graph give us measurable properties of this infinite graph, and vice versa. If we can prove theorems about the size of measurable graph parameters of this graph, we get information about the individual finite graphs, which we're taking the limit of. So that all of these things I haven't defined carefully, but the point I want to get across is that many different areas of mathematics were studying problems like this. And it's only rather recently, maybe in the past decade or so, that some of these groups of people have found each other, realized we were all studying pieces of the same general theory, and came together to share ideas and techniques. And I want to tell you something about this theory and its applications recently. So let's start with a very simple example. Maybe the easiest example that shows there's a difference between measurable graph combinatorics and the more classical idea where we just take any solution to a problem, say, assuming the axiom of choice. Let's make an infinite graph in the following way. The vertex set is going to be all the points of the unit circle. So this is an infinite set of vertices. And we'll fix an irrational rotation of the circle. By irrational rotation, I mean rotation by an irrational fraction of pi, so that if I take any point and apply the rotation any finite number of times, I'm not back to the point that I started at. So I'll make a graph now where the edges are in between each point x and its image, t of x, and its preimage under this irrational rotation. So if I take a single connected component of the graph, it looks like a bi-infinite line of vertices of degree 2. So assuming the axiom of choice, I can choose a single point from each connected component, color it, say, red, and color all of its neighbors blue, and repeat this pattern to obtain a two coloring of the graph. By coloring here, I mean proper coloring, like the four color theorem, a way of assigning a color to each vertex so that no two adjacent vertices receive the same color. So what I want to show is that if we demand now that the coloring is Lebesgue measurable, then there is no Lebesgue measurable two coloring of this graph. And the reason is an easy argument of ergodic theory. So let's begin by assuming that there is such a Lebesgue measurable coloring for a contradiction. And I'm going to let A be the set of points assigned the first color. So since the coloring with two colors has to alternate between them, this set A of points assigned the first color has to be disjoint from the image T of A under this irrational rotation of the set. And these two sets, all the points assigned the first color, and the image under T, which has to be all the points assigned the second color, have to partition all the points of the circle. Since T is a measure-preserving map, we therefore have that A and T of A must have equal measure, half the measure of the circle. However, if I consider the map T squared, that's also an irrational rotation by an angle that's twice as large as the angle defining T. And T squared of A is equal to A. By definition, an ergodic transformation is one so that any measurable set invariant under the transformation is either null or co-null. And it's an easy fact of ergodic theory that irrational rotations are ergodic. One can prove this, for example, by noticing that each orbit under an irrational rotation of applying T, T squared, T cubed, and so on to a point is dense in the circle, and then using the Lebesgue density theorem. So since T squared is an ergodic transformation and T squared of A is A, we must have that A is either null or co-null. But we just proved it has measure a half, and that's a contradiction. The first place that I know of in the literature where this proposition is written down exactly is a paper of Falconer from 1981. He was studying the unit distance graph in the plane, and this was used as a lemma to show that there is no Lebesgue measurable four-coloring of all of R squared, so that any 2 points at unit distance have to receive different colors. But if you just take this lemma by itself, it's a very easy example showing that measurable graph combinatorics can have different answers than just classical combinatorics without assuming any measurability conditions. Okay, I want to define precisely now the objects that we're going to consider. A Borel graph is a graph whose vertex set are all the elements of some Polish space that is separable, completely metrizable space. Spaces like R to the K, or the unit interval, or the Cantor space. And the edge relation of the graph we require to be a Borel subset of V cross V. So in our irrational rotation example, the edge relation is closed. If you take a sequence of pairs of points that are related, and they're all distance apart from each other given by the irrational rotation, so is the limit. But we're more generally allowing any Borel relation, a set as Borel, recall, if it's in the smallest sigma algebra containing the open sets. And sigma algebra here means it is closed under countable unions, intersections, and complements. This is okay, so why choose Borel graphs, or in a minute, why choose Borel colorings of them? Well, the Borel sets have this nice sort of Goldilocks property that they're large enough to contain enough closure properties to make a nicely robust theory. However, they're also small enough to be, in a sense, concretely definable, and to have nice regularity properties, like being Lebesgue measurable or Baire measurable, for instance, if we want one of these broader measurability notions. So the Borel sets are a commonly considered class of definable sets studied in descriptive set theory. And by choosing to study Borel graphs, I'm going to be concentrating, at the beginning at least, on the objects that in some sense we can concretely define. And if we have a definable graph, when can we find a definable solution to a coloring problem on it, or a matching problem, or some other combinatorial problem? Okay, so let's talk about some more elaborate kind of constructions and proofs that in some situations show us that finite combinatorics has the same behavior as measurable combinatorics, and other cases where it doesn't. Recall the degree of a vertex in a graph is its number of neighbors, and I'll be focusing in this talk on graphs of bounded degree. So in finite graph theory, one of the first theorems you learn about proper coloring is that if you have a graph of degree at most d, so every point has at most d neighbors, the graph has a d+1 coloring, a coloring with d+1 colors. And the proof is a very simple greedy algorithm. Just color the vertices one by one. And each time when you color and extend the partial coloring you've defined so far, in the worst possible case, you've already defined the color of each of your neighbors, but you have only d neighbors, and there's d+1 colors. So there's an extra color to use that you haven't already used for one of your adjacent neighbors. The very first paper in descriptive set theory to sort of systematically consider problems of trying to definably color or measurably color Borel graphs was a paper of Kekker-Slutsky-Todorcevich, who proved a bunch of fundamental results in the subject. And one of the simple results they prove in that paper is that there's a definable analog, a Borel analog of that theorem. And you can prove it by basically adapting the same greedy algorithm. If you have a Borel graph of degree at most d, it has a Borel d+1 coloring. And one proof of this is to fix some countable basis of sets in your space of vertices. And since each point in the graph has finitely many neighbors, some basic open set separates it from its set of neighbors. And so inductively, if you take the ith basic open set and color all the vertices in it whose neighbors are not in that basic open set, the least color not already used by one of its neighbors, you obtain a Borel coloring of the graph. And even if it's not immediately clear to you that that is Borel, at least it should be clear that that is a definable coloring, one that you can concretely make without the axiom of choice. And if you believe this thesis that the concretely definable sets are exactly the Borel sets, then that should be indicative of what should happen in definable combinatorics. So maybe the next easiest fact in finite graph theory is Brooks's theorem. And Brooks's theorem is about when we can improve this obvious upper bound of d+1 colors for a graph of degree at most d. So Brooks's theorem says that if you have a finite graph, and again, each point has at most d neighbors, then actually you don't need d+1 colors in most cases. You can decolor the graph. But there are two exceptions. If you have a complete graph on d+1 vertices, so that is take d+1 points and render every pair of points adjacent, then since any 2 points have an edge between them, this is the complete graph, for example, on 5 vertices, they would all have to receive different colors. So in this graph, every point has 4 neighbors, but all the different points have to receive different colors. And so it has no 4 coloring. Its chromatic number, if you like, is 5. So this is an example where we can't do better than this greedy upper bound of d+1 colors. And the other example is odd length cycles in the case of d = 2. Right? But Brooks's theorem is that these are the only 2 exceptions, that every other graph where each point has d neighbors has a decoloring. So the sort of definable analog of that theorem is not true. In fact, there are much more complicated dynamical phenomenon that lead to graphs having high measurable chromatic numbers. So in fact, Kekker-Slutsky and Todorovich's greedy upper bound is optimal, even the case when the graph is acyclic. So these graphs that are constructed in this theorem are quite natural, actually. They come from taking a group which is a free product of cyclic groups of order 2 and taking the free part of the Bernoulli shift of these groups. And those give acyclic graphs, roughly because the Cayley graph of the group I just described is acyclic. And the proof that there's no Borel decoloring uses Martin's famous theorem of Borel determinacy. This is the theorem that says if you have an infinite game with a Borel payoff set, then there's a winning strategy in the game for one of the 2 players. And the game that's set up in this theorem is a game to construct an element of this Bernoulli shift space where one player defines the point on some of the elements of the group and the other player defines the remaining the point on the remaining elements of the group. And the outcome of the game, who wins, depends on what color is assigned to the point they construct together. And then a fairly easy kind of strategy stealing argument can be used to construct 2 adjacent points in this graph that receive the same color, assuming you're only coloring with D colors, and hence get a contradiction. Martin's theorem of Borel determinacy has this interesting metamathematical property that it requires a vast amount of set theoretic power to prove. Even though it's a theorem just about subsets of the real numbers, it requires the existence of infinitely many, or in fact, uncountably many iterates of the power set of the reals to prove. And that's a vast amount of set theoretic power to prove such a concrete theorem. And it's open whether this theorem also has the same property in reverse mathematics, whether there's, it requires, like the Borel determinacy theorem, the existence of infinitely many iterates, or uncountably many iterates of the power set of the reals. Okay, so there's not a Borel analog of Brooks's theorem. However, if we weaken the notion of coloring that we consider just a little bit, and instead consider when we have a Borel probability measure on our set of vertices, and we ask instead for a mu measurable coloring, then we do have an analog of Brooks's theorem. Suppose you have a Borel graph of degree at most d, and it doesn't contain a complete graph on d+1 vertices. Then there's a mu measurable decoloring. And the coloring is made in a way that's a little similar to how Brooks's theorem is proved. If you know the proof of Brooks's theorem using what are called Kemp chains in finite combinatorics, there's an object called a one-ended spanning subforest that's made in the infinite setting that allows you to perform a similar sort of coloring algorithm to Brooks's theorem to prove the result. And that proof, that algorithm converges almost everywhere. And that's what leads to mu measurability here. It's not an accident that the 2 positive examples that we've seen, this greedy algorithm, which is adapted to the Borel setting, and this algorithm for proving a measurable Brooks's theorem, which is adapted to the mu measurable setting, both those proofs for constructing measurable colorings are based on algorithmic ideas. And a simple reason for that is that if you have an algorithm to solve a problem, it will give you an explicitly defined solution. And a little more deeply, the connection between definability and computability in logic is a deep and long studied one. And so it's not surprising that if we want explicitly definable colorings, computability should be involved in some sense. But I want to mention here that there are tighter and very new and useful connections between measurable combinatorics and the theory of distributed computing, in particular the local model of algorithms in theoretical computer science. This area studies large finite graphs. Imagine the internet, say, and all the connections between the computers on it. And in this large finite graph, we assume at every vertex there is some computer or processor that's simultaneously running. All these processors are simultaneously running the same algorithm, and they want to globally solve some problem, like coloring the graph, for example. And the complexity of this algorithm is measured in terms of how many rounds of communication need to happen between adjacent vertices to solve the problem. And precise theorems have been proved saying that there are measurable solutions of certain sorts to combinatorial problems if and only if there are efficient local algorithms to solve the same problems in theoretical computer science. And this is very recent work from the last year or so, people like Anton Bernstein and others in this area. Okay, so I want to talk, though, about another way of running algorithms on Borel graphs, and that is the technology of hyperfiniteness. We say a Borel equivalence relation is hyperfinite, and the equivalence relations we'll apply this to are the connectedness relations of our Borel graphs. If and only if it can be written as an increasing union of subequivalence relations with finite classes. And so a different way of saying this is that a Borel graph has a hyperfinite connectedness relation if and only if it can be written as an increasing union of subgraphs that are Borel with finite connected components. And such a way of sort of approximating our Borel graph from below by graphs with finite connected components is very useful, because if you try and run an algorithm on an infinite graph, it may not converge in the same way you can prove that it does for finite graphs. But if your graph is hyperfinite, you have an obvious way of trying to adapt the algorithm. You can run the algorithm or small modifications of it on each of the finite connected components in these subgraphs that union up to G, and hope that all these algorithms converge in the limit. And that's been a useful and important way of running algorithms on Borel graphs. However, the problem of what graphs or what Borel equivalence relations more generally are hyperfinite is deep, and there are many open questions. And what I want to do next is talk about some problems of hyperfiniteness that are related to measurable combinatorics. I've tried to convince you already that hyperfiniteness is useful for doing constructions in measurable combinatorics. And I also want to convince you in a minute that measurable combinatorics gives you tools for proving hyperfiniteness results. So there's a sort of feedback loop happening here, that the more we learn of tools and techniques of measurable combinatorics, the better we're able to prove hyperfiniteness results, which in turn let us prove more combinatorial results. Okay, so the study of hyperfiniteness has a longer history in descriptive set theory than graph combinatorics, for example. It's been a major program in the subject since the late 80s. And the general idea of the study of Borel reducibility of equivalence relations has been to try and understand the relative difficulty of different classification problems in mathematics. And by that, I mean the relative difficulty of taking some notion of equivalence, like homeomorphism of compact two manifolds, or conjugacy of measure-preserving transformations or isomorphism of Banach spaces, and try and understand the relative difficulty of trying to classify those problems by invariance. And this area is maybe analogous to how in theoretical computer science, we study the relative complexity of various problems by polynomial time reduction. We want a way of saying this classification problem is strictly more difficult than this sort of classification problem. So for instance, if you want to classify complex n by n matrices up to similarity, you can do that with Jordan normal forms. But if you want to classify, say, isomorphism of Banach spaces, it's impossible to do that using finite tuples of complex numbers as invariants. And so that classification problems is strictly more difficult than classifying matrices up to similarity. And the field has had success in trying to calibrate the complexity of particular problems of interest to working mathematicians and show, for example, these problems can't be classified using these invariants because the problem is more complex than the invariants give you space to solve with. So a spectacular example comes from Elliott's classification program in C-star algebras, which originally sought to classify a certain class of C-star algebras using invariants from K-theory. And the work of many mathematicians, and particularly, I guess like I mentioned, Turnquist and Farah and Toms, showed that the classification program as it was originally conceived was impossible because the objects they were seeking to classify were more complicated than the invariants they were trying to use, which were countable structures. And that it was shown that any class of countable structures couldn't be used as invariants. Okay, so that's the general program. And I have this picture from a nice survey article of Matt Foreman in the notices about this, showing a few examples of equivalence relations and some relations between them. But I want to focus here on hyperfiniteness, which was originally defined in this study as a simplicity notion for equivalence relations. If I were to draw hyperfiniteness in this picture, it would be way down at the bottom here. And in fact, there's a beautiful dichotomy theorem of Harrington-Kekker-Slouvaux, which shows that in a precise sense, the simplest non-trivial equivalence relations are the hyperfinite ones. By non-trivial here, I mean they can't be classified using just real numbers as invariants. Okay, so that's some motivation for what hyperfiniteness is and why it matters to descriptive set theorists. I want to talk in a slide about an important open problem about hyperfiniteness, but to do that, I need to define the notion of amenability of groups. So I'll say a discrete group is amenable if there's a finitely additive probability measure on the full power set of the group. So every subset of gamma, which is invariant under left multiplication. So equivalently, this amenability condition can be described finitistically. It's equivalent to saying that for every finite set S and epsilon greater than 0, there's some larger finite set F that doesn't expand much under multiplication by F. So in fact, this is the same roughly as saying that every Cayley graph of the group gamma has a 0 isoparametric constant. This is, if you like, the size of the boundary of F in that Cayley graph. So this is a non-expansion kind of property for gamma. It's kind of a tameness property. And the definition traces back to von Neumann, who made it in reaction to the Banach-Tarski paradox. Incidentally, these two definitions are equivalent because we can take the uniform probability measure on F and take an ultra limit of those probability measures to make this sort of invariant measure in my original definition. Okay. So some important examples of amenable groups are finite groups, abelian groups, and solvable groups. And the canonical example of a non-amenable group is the free group on 2 generators. But if you haven't seen amenability before, what I want you to remember about it is that it has become a crucial dividing line in dynamics. Amenable groups have actions that in precise senses are tame and concretely classifiable and simple in various ways, whereas non-amenable groups have wild, unclassifiable, paradoxical actions. And theorems of this sort have been proved in areas like ergodic theory and von Neumann algebras. And there are conjectures like this in topological dynamics and C-star algebras, for instance, which significant progress has been made on in recent years. But I want to talk about a conjecture of this sort, that amenability can be is a simplicity notion, and non-amenability leads to wildness in this setting of classification of equivalence relations in descriptive set theory. So the open problem that I want to talk about is Weiss's question. Suppose we have a Borel action of a countable group. We can form the orbit equivalence relation of this action. We render 2 points equivalent if they're in the same orbit of this action. And Weiss's question is whether every such orbit equivalence relation generated by a countable amenable group must be hyperfinite. If you like, roughly, this is asking whether this group theoretic and dynamical notion of simplicity corresponds exactly to this descriptive set theoretic notion of simplicity in terms of being the easiest possible equivalence relations that are non-trivial to classify. There's been lots of progress on Weiss's question. It has a positive answer, for example, for actions of the group of integers, z to the n, more generally for groups of polynomial growth. And then for countable abelian groups, locally nilpotent groups, and most recently polycyclic groups. I will say a few words about what these proofs look like. And in particular, to me, there's a kind of a dividing line in techniques and complexity between these results and the ones that came afterward. The first three results here were proved using ideas that come from measurable combinatorics, coloring to find a independent set of points of far distance that's maximal with respect to having some large distance from each other, and then forming what I would call Voronoi regions around those points, and then using those as the building blocks of equivalence relations to witness hyperfiniteness, and using some packing arguments to show eventually you union up to yield the equivalence relation that you like. But those techniques stop working when the groups you consider aren't finitely generated anymore. And that's the big breakthrough that was made by Gao and Jackson in 2015. Instead of trying to build a sort of coherent sequence of subequivalence relations unioning up to the full equivalence relation, instead they try and build these kind of anti-coherent sequences of coverings of the group with far apart facial boundaries. And then they take tail intersections to get a hyperfiniteness witness. And that technique was expanded on by Seward and Schneider to handle locally nilpotent groups. And most recently, we've proved that polycyclic groups all have hyperfinite actions. And maybe I can say something about this very last result. Eventually, we realized that these two approaches of the first three results here, z to the n, and groups of polynomial growth, and what came after these ideas of Gao and Jackson were really two sides of the same coin, but equivalent in a very non-trivial way. And hiding inside all of these proofs really was Gromov's notion that originally came from geometric group theory of asymptotic dimension. Asymptotic dimension is a sort of coarse version of Lebesgue covering dimension in topology that you can use to understand the geometry of groups. And by adapting these notions to the Borel setting, it turns out you can still prove many of these equivalent definitions of finite asymptotic dimension are the same using tools from measurable combinatorics. But the equivalence is not at all straightforward. And the different guises that asymptotic dimension has are precisely what is needed to understand the jump from the first three results to the last three. And then once you realize that all these results are sitting in this beautiful abstract framework, finding a Borel witness to finite asymptotic dimension can be reframed as a sort of generalized coloring problem on Borel graphs that come from these group actions. And you can solve those coloring problems using tools that have been developed from measurable combinatorics. So I want to put these two things that I've talked about now together. So I talked a little bit about the theory or the beginnings of the theory of measurable combinatorics. And then I talked about this application to understanding hyperfiniteness in this program of Borel reducibility of equivalence relations. And the last thing that I want to talk about today puts these two pieces of mathematics together. And in particular, we get new explicit solutions to Tarski's circle squaring problem. But I want to give a little context to the problem first. The famous Banach-Tarski paradox says that assuming the axiom of choice, you can take a single unit ball in R3, partition it into finitely many sets, rearrange them by isometries, and obtain a partition of 2 unit balls. So using the terminology of the area, we would say 1 unit ball and 2 unit balls are equidecomposable by isometries. Okay, however, in 2 dimensions, the analog of the Banach-Tarski paradox is not true. It's not the case that 1 unit disk in R squared is equidecomposable with 2 unit disks. And the reason for this, and part of the original motivation for proving the Banach-Tarski paradox, was the question of to what extent we can extend Lebesgue measure to measure all subsets of R squared or R cubed, and still have some of the nice properties of measures that we like isometry invariance, or finite additivity. Of course, the existence of Vitali sets rules out countably additive isometry invariant measures on these spaces, but it's an interesting question to weaken the notion to give, for instance, finitely additive measures, which leads to the theory I'm about to discuss. Or, of course, set theorists also weaken this notion by throwing out isometry invariance, which leads to the theory of measurable cardinals. The difference, incidentally, between R squared and R cubed has to do with the group theoretic difference between their isometry groups. R squared has an amenable isometry group, whereas R cubed has a non-amenable one. And that's the difference that gives the existence of these Banach measures. Okay, so based on this difference between R squared and R cubed, and the fact that because there are these Banach measures, if you take any measurable set in R squared and split it up into finitely many pieces, by finite additivity of the measure, the sum of the measures of those pieces still has to add up to the measure you started with. And that's true even after you arrange the pieces. So you can't equidecompose any 2 sets of different measure in R squared. So Tarski wanted to know to what extent actually are equal measure and equidecomposability the same in the plane. And he formulated a specific question like this: are a disk and a square of the same area equidecomposable? So the circle squaring problem was a lot more difficult, it turns out, to answer than the Banach-Tarski paradox, and it remained open until it was solved by Laskevich in 1990. Assuming the axiom of choice, Laskevich showed there is an equidecomposition of a disk and a square of the same area in R squared. But because there's no paradox of measure like there is with the Banach-Tarski paradox, it left open the possibility that you could perform such an equity composition with measurable pieces, for instance. And that was proven in 2017 that you can Lebesgue measurably equity compose the circle and the square, once again assuming the axiom of choice. And then later the same year, we proved that it's in fact possible to explicitly define a solution to the circle squaring problem using Borel pieces and not appealing to the axiom of choice at all. And even more recently, Mattei, Noel, and Perkirko have shown that you can find Borel pieces that are even Jordan measurable. And they have nice fractal dimension properties. Their boundaries have upper box dimension less than 2, and they're in fact Jordan measurable. And this is the current state of the art in how simple we can find a circle squaring. So I want to say a couple words about what these proofs look like. So the proofs use tools from measurable combinatorics, and the reason to start with that should make sense is that you can reformulate an equity composition problem as a perfect matching problem. You make a graph, for instance, where the vertices of the graph are a disk, all the points of a disk, and all the points of a square. And you put edges between 2 points if one of the isometries you hope to use to do your equity composition moves 1 point to the other point. So it's possible to make a nice Borel graph like this and prove that there's a perfect matching of this graph if and only if there's an equity composition of a circle and square. And if the perfect matching has measurability properties, that means the pieces of the circle squaring are measurable. The other tool that's used in the proof is progress on Weiss's question, special witnesses to the hyperfiniteness of actions of z to the n. Z to the n because if you act on the plane, or in fact the space that eventually is used as the torus, then the translation, any two translations commute with each other and hence define a z to the n action. Okay. We're running a little low on time, so the last idea that I want to draw out is that using some of the equivalences between finding flows in graphs and finding perfect matchings and the Ford-Fulkerson algorithm and the Max-Flow-Min-Cut theorem. In fact, the proofs use flows in graphs as a first step towards finding equity compositions. The flows have nice properties that make them easier to work with in measurable combinatorics. For instance, the average of flows is flows, or flows you can approximate in countably many steps where you make the error in satisfying flow conditions go to 0. And then there's this process of rounding these flows using things like the Ford-Fulkerson algorithm on this hyperfiniteness witness to actions of z to the n, which is used to eventually define an equity composition. So here's a sort of fanciful picture of what such a circle squaring looks like. This isn't exactly what happens in the paper. This is sort of a pixel level approximation. I'll end there. Thanks very much.
Thanks, Andrew. Let me ask a very quick question, one quick question. How low do you think the Borel complexity of the pieces in the Banach-Tarski can be pushed? For example, can the pieces be made both F sigma and G delta, each piece?
Yeah, it's a good question. And this recent theorem gets quite close to answering your question. The pieces in their equity decomposition are finite Boolean combinations of F sigma sets, that is countable unions of closed sets. Making the pieces one step lower in the Borel hierarchy, as you said, delta 0, 2, F sigma and G delta, I think is a reasonable kind of limit to what we know is possible, since it is a theorem that you can't square the circle using extremely simple pieces. There's this notion of scissors congruence due to that comes from work in the 60s, and you can't show that the circle and square are scissors congruent. So your question is open, but this theorem is quite close in Borel complexity.
Mm-hmm. All right, thank you.
Thanks.
Well, we are on a strict schedule, so thanks, Andrew, again, and this concludes the session. So we are done.
Yes.